All right, so now we'll talk about the Bregman divergence and the exponential family. So we've already observed that if you have an exponential family of probability distributions, there's this normalization factor, it's like which is in the exponential, and it has the property that it's a convex function, right? So in an exponential family, the normalization factor phi of theta is convex. So we know it induces a Bregman divergence, right? Which I denote by d phi theta prime. Right, so it's natural to ask sort of the inverse question, right? So it is natural to ask the converse. Which is to say that given a Bregman divergence, is there a corresponding exponential family, right? So it turns out that there is, okay? So let's look at the following. So you consider a random variable. Let's call it x. And so it's like, so in particular you have, what you're given basically is this convex function. It's like on the theta variable, right? So so that defines a point. Let's call it eta prime equals to x, right? In the eta coordinates of a dually flat manifold. Given by this convex function. Okay. And then let theta prime be its theta coordinates. All right. So I can write the phi divergence from theta to theta prime as follows. Where again, theta prime is the coordinate associated with this point x, but in the theta coordinate system, right? So this is phi of theta plus psi of theta minus theta dot x. Okay, where this is, if you recall, it's like the convex dual, it's like of the function. So with this, it's like we can define a probability density function. Which I'm going to express in terms of the divergence. All right. So so we have some probability distribution depending on a random variable. It's like, and then this theta coordinate. Okay, and I'm going to write this as the exponential of minus the divergence from theta to theta prime plus this normalization function and because of the form of the divergence which we've written here, this is just the exponential of theta dot x minus phi of theta. Right? So where theta prime is determined from x as the theta coordinate associated with a point eta prime. It's like an eta coordinate system, which is just x. All right. So more or less in the dual coordinate system, it's like we look at the point x, and then we find it's associated. It's like primal coordinates, when we call that theta prime. Okay. All right. And this particular form of the Bregman divergence, if you recall, involves this use of the primal convex functional, the dual convex functional, and the sort of the product or the inner product, if you will, it's like between the primal and the dual coordinate, right? And it just so happens that because the way we set it up, it's like the dual coordinate is x, right? Which is what happens here. Okay, so, and that clearly is the form of a exponential family. All right. So from this, so it's clear that we have an exponential family derived from the Bregman divergence. So I can restate the problem in the following way. So let's see how we can re-envisage this problem. So the problem can be thought of in this way. So given a convex function, phi theta, I want to find a measure d mu of x such that the following is true. Such that this convex functional is the log of the integral of the exponential of theta dot x d mu. And if you recall, it's like that condition is really just a normalization condition. All right. So that condition can be written equivalently as the following. That's the exponential of this convex function is equal to the integral of the exponential. Yeah, I'm just taking the exponential on both sides, right? So I'm not really doing anything fancy here. Okay. All right. So this is the inverse Laplace transform. Okay. So the bottom line again is that there's this bijection between exponential families and Bregman divergences. Okay. So let me just state that. So the theorem is as follows. There is a bijection between regular exponential families and regular Bregman divergences. Okay. So let's make a few remarks about that. So what this is basically saying is that given a Bregman divergence, there is a corresponding family of probability distributions for which the Bregman divergence in question is really just the KL divergence for that family. All right. Okay. Okay, so that's basically what I wanted to say here, and then it's like what we're going to see following this is an application of various applications. It's like of the Pythagorean theorem. It's like which relates it to various notions of statistical properties. It's like our probability distributions. So we'll see that in a little bit. So I'll stop here.